This is chapter 13, homework for dynamics. The first problem asks to find the horizontal distance that the bucket will swing when the crane stops, starting from 10 feet per second. You use these two equations and plug it into here. We have m, and we can cancel those out and then bring over g and then solve for h, and then you get 1.55 feet. And then using this diagram, y is 30 minus h, because we know that this length is 30, and then we get 9.52 feet. The next problem is asking for a truck that is going uphill at 2% grade, and it's asking for the forces on the wheels of the cab and the force in the coupling between the cab and trailer. So the first part will need the combined mass of the two, and then we use this equation right here for energy, and then plug in for FT. I forgot to draw a free body diagram for this one, but we have our weight and our velocities, and then we get an FT of 7.4 kilonewtons. And then for the second part of the problem, it's asking for the coupling, and then you just use the mass of the cab for this part, and then you get a 5.56 kilonewtons of tension. The next problem is asking for how long it will take, or the average force at the wheels of the cab. No, this is the train problem. So we have a normal force going up at each cab, or at each train, I guess. We have the weights of them, and we have the velocity, and then the brakes are applied to the first train, and we need to solve for the distance required to bring the train to a stop. So we solve for FA using this equation. It's 28 kips, and then we have the velocity, and then we use the energy equations, and we get that x equals essentially 280 feet. And then the next part of the problem is to solve for the force in each coupling. So between the trains, so for train A, it's in compression. We use the free body diagram. So equal to 0, and we get FAB equals 19.38 kips in compression. And then similar process for C, and we get FBC is 8.62 kips. For problem 4, it's asking us to determine the angle theta at which the rope will break when we know that the max tension it can withstand is twice the weight of the ball, or of the sphere. And then we use this diagram and these energy equations. We can cancel out m because it's throughout the equation, and then we get v squared equals 25 plus 39 sine theta, and then we know when T max is 2, then that will break, so then we plug in, sorry, I just broke my pencil. And then we plug in v squared, and then we get theta equals 14 degrees. The next problem has 1,000 skiers moving per hour up a ski lift, and we have all these givens, and then we want to find the average power and the required capacity of the motor. So the average power is solved using this equation. These are all known, so then we know that it's 57.2 kilowatts. The max power at 300% overload is 100 plus 300 divided by 100, which gives us 300%, times our average power, which is 229 kilowatts. And then you divide that by 0.85 to get the required capacity. The next problem is asking for the velocities as it passes through B and C of this system right here with a collar with no friction, and we have our constants. And then what we have to do is we solve for the x of like the spring at different points. We know that at C it's uncompressed, so it's 0, but then we solve for the others. And then we solve for VAE, so the energy required at each one. And then we solve for G, and then we get back up to here. These are just the precursors to solve for A and B. So then A is just TA plus VA equals TB plus VB. And we get VB equals 2.48 meters per second. And then B is V equals 1.73 meters per second. 7 is asking for there's a spring, and this block is coming up to the spring, and we want to know the max additional deformation of the spring to bring a package to rest. So it's coming down, and we want to know how much it's going to deform for it to rest. So we have theta, we have this equation, we plug it in using the energy equations. I don't want to explain it too far, because we're running out of time, but and then you get an x equals 2.69. With using this algebraic equation, you get 1 negative. All right, for the second part of this homework, it's covering momentum, and one sec. And this problem is asking for the magnitude of braking force for a truck that's going uphill, like onto a safety ramp. So it's going uphill, and we want to know the magnitude of braking force and the time for the truck to stop. So I have this free body diagram right here. We have the mass of the truck. We have these momentum equations. We have our force right here, and we have this equation to solve for time. We have the total time, which is 9 seconds, but then we want to subtract the time that they gave us here to get the additional time, which is 3 seconds. The next part of the problem, the next problem is asking to find the time where the velocity of color B will be 2.5 meters per second. So we know that there's no friction, and I drew out this I guess system of free body diagrams. Usually it was laws, and then ended up with this equation, which then we use for this part of the problem. And this is block A, doing similar processes prior, and then for part A, we are solving for time. So we add those two equations together, and it will cancel out t, and then we can just solve for t. which is 0.55 seconds. This answer varied from the solution, but I think this is right because I'm using this equation, and then I got 31.25 using t, or setting t equal to 0.55. All right, so the next problem, it's a ballistics, a ballistic pendulum problem, where we have the maximum angle is 60 degrees, and we want to find B naught, the impulse imparted by the block on the block, and of course on the cord immediately after impact. So we have this momentum equation to explain this system of reactions. So at A, or for part A, we are substituting the equation and solving for V naught. And then for the second part, part B, we're writing the impulse moment equation, which is F dt, and then solving for after impact, we're solving for the force, which is T, and then we get 19.74 newtons. All right, the next problem is a series of steel spheres are being swung onto each other, and we're solving for the velocity of A and B immediately after the collision, velocity of B and C immediately after the second collision, and so forth. So for A, we know that the total momentum is conserved, and then we know the relative velocities, so we can use those equations, solve for them simultaneously, and get these two. And then the next problem, I have this little diagram right here, or the next part of the problem. We also, we still know that the total momentum is conserved, and then using V prime B, we plug that into the equation, we have the relative velocities, and then we substitute V prime B again. And then we'll solve simultaneously and get these two solutions. For N balls, we can rewrite this equation into this, and then essentially just replace the 3 with an N and get this equation. And then for the next part, we just plug in 8 for N, because we have N equals 8, and then we know that E equals 0.9. And then for the last problem, we have a 1 kilogram block and a 0.5 kilogram sphere. We have our constants, and we want to solve for the max height of the sphere and the distance traveled by block. So similar process again. We know that total momentum in the horizontal direction is conserved. We use the relative velocities, and then we solve for V prime B and V prime A simultaneously. And we get these two velocities right here. And then for part A, we're solving for H. We use this equation. We know that V2 equals MA GH, and then we just solve for H here. The next part, I have my free body diagram. And it's using work and energy. We're solving for X. We use this equation and plug in X in terms of the friction, and we get an X of 0.0544.